Now we have the conormal points of an ellipse. So in the case of parabola, we said that there can be three normals drawn from any point hk to the parabola. So in the case of ellipse, we are going to have that we can have four normals from any point outside the ellipse. We can have four normals. So we have uh, the equation of the normal at any point theta, that is a cos theta b sin theta, is given by ax by cos theta minus by by sin theta equal to a square minus b square. So from there also we started with only the parametric form of equation of normal at t. Here at theta we are considering this theta is called eccentric angle. So you have, when we consider an ellipse, when we consider any point p of theta, by theta I mean eccentric angle, and this is nothing but a cos theta b sin theta. So we consider the equation of the normal at p of theta, and that is given by x by cos theta minus by by sin theta equal to a square minus b square. Let it pass through the point hk. So we have this, and we know that cos theta is given by 1 minus tan square theta by 2 by 1 plus tan square theta by 2. So secant theta will be, by taking tan theta by 2 as t, we can have this to be 1 plus t square by 1 minus t square. So this ah secant theta will now become ah 1 plus t square by 1 minus t square. In the same way, sin theta, we know that it is given by 2 tan theta by 2 divided by 1 plus tan square theta by 2. So that becomes, when we consider cosecant, it will be 1 plus t square by 2t. So that is what is written here, and then further this has to be simplified. So we will, when we collect the terms containing t power 4, t cube, there is no t square term, that means 0 into t square we have. There is a term with t and the constant term. Now this being a fourth degree equation in t, it will have four roots. We shall name them as t1, t2, t3, so that the sum of, actually in this we were trying to prove that there can be four normals. So we are stopping with that. But when we consider the result that the sum of the theta i's, the eccentric angles, is an odd multiple of pi radians. It is an odd multiple of pi radians. So to have that, we just continue the same discussion. If theta 1, theta 2, theta 3 and theta 4 are the eccentric angles of 4 points on the ellipse such that the normals at them are concurrent, that is, they are conormal points, then the sum of theta i's is an odd multiple of pi radians. That is, the sum of the eccentric angles of those points, conormal points, is an odd multiple of pi radians. Odd multiple of pi radians, odd multiple, odd number. So odd multiple of pi means this is what we have to show. Theta 1 plus theta 2 plus theta 3 plus theta 4 is equal to this. This is what we are trying to prove. So again, all the statements or the steps that we had in the previous discussion, again they have to repeat. Consider the equation of the normal, the parametric form, and then let it pass through hk. Rewrite fourth degree equation, four roots t1, t2, t3 and t4. So you get first the relation between the roots and coefficients, a relation between the roots and the coefficients. Roots and coefficients. So that's from theory of equations. We are having this. There is no t cube term is there. So minus, always minus, plus, like that. So minus of, you have this divided by bk. and there is no t square term, 0 into t square. So you get this to be 0. And the third one, sum of the product of the roots taken 3 at a time, and then the product of the roots. Product of the roots, if you look at this, minus bk by bk, so minus 1 you get. Now, so your aim is to have theta 1 plus theta 2 plus theta 3 plus theta 4 as something. Okay. So in order to have this, we cannot directly proceed with that. So we'll have to consider the tan of that. So but here we have got the relation with theta 1 by 2, theta 2 by 2, theta 3 by 2. So we'll have to consider that. So tan of this, it has to be remembered. This is tan of a plus, when you have tan of a plus b, we know that it is tan a, tan b, tan a plus tan b divided by 1 minus tan a, tan b. So likewise, when we have tan of a plus b, we have formula, and this is a, something like this, a plus b plus c plus d. So this can be crudely remembered in this way. So whenever you have tan of, how many ever terms that you have, let it be, you have first 1 and then s1, then come here s2, then go up s3, then come down, where you have to stop. When you have 4 terms here within the bracket, you have to stop with 4. If you have 5 means, again you have to go up s5, like that. So then first with plus sign, then with minus, first with plus, then with minus, then with plus alternatively. So in that way this can be easily remembered, s1 minus s3 by 1 minus s2 plus s4. We just substitute the values. This s1 is the sum of the roots, this is sum of the product of the roots taken 2 at a time, taken 3 at a time, and product. So when we see the denominator, we have s2 to be 0 and this one to be minus 1. So the denominator vanishes. But we have to ensure that the numerator is non-zero. When you consider s1 minus s3, you can compute and actually it is non-zero. So we have tan of something to be infinity. So that something should be, this should be n pi plus pi by 2, because tan 90 is infinity. Tan 90 is infinity. And tan pi plus 90 is infinity, and so on. So tan pi plus and 2 pi plus, and so on. So in general, tan n pi plus pi by 2. So you have, and therefore this argument you have to be n pi plus pi by 2. On simplification, you get, taking LCM, 2n plus 1 pi by 2, 2 can be cancelled, you have this. So it's an odd multiple of pi radians. Now we will see a few examples, worked out problems on the normals in the case of ellipse, so that then we can move on to concyclic points. So here the first one, if alpha, beta, gamma are the eccentric angles of 3 points on the ellipse x square by a square plus y square by b square equal to 1, the normals at which are concurrent, then we are asked to prove something. So if alpha, beta, gamma are the angles of 3 points on the ellipse, so we shall consider the normals at these points passing through HK. Actually 4 normals we can draw, so we shall take the fourth one to be delta, eccentric angle. Now we know the relation between the roots and coefficients. So we had S2, which is summation T1 T2 to be 0. T1 actually here stands for tan alpha by 2. T2 means tan beta by 2. It goes like that. So this is T1, this is T2. So you have tan alpha, summation tan alpha by 2, tan beta by 2 to be 0, and product of the roots. This is what you have, equal to minus 1. Now for convenience sake, they are denoted as T1, T2, T3 and T4. Your tan alpha by 2, tan beta by 2, tan gamma by 2, tan delta by 2. Now eliminating T4, because in the picture, that is, I mean here we don't have delta term, that has to be eliminated. So what is the term which is related with delta? It is T4. So we'll have to eliminate T4 from 1 and 2. So we have this on expansion. This on expansion gives you 6 terms, 4C2 terms. So it is T1, T2, then plus we have T1, T2, T1, T3, T1, T4, plus T2, T3, T2, T4, plus T3, T4. So T1, T2 is retained as such. We know that T1, T2, T3, T4 is minus 1. So wherever you have T3, T4, you can replace it by 1 minus T1, T2. So that is, we have accounted for 2 terms of the 6 terms. Then coming to this one, T2, T3, that is retained. And then T1, T4 we have, So this one, that is replaced by minus, using this, minus 1 by T2, T3. So we are now left with only these 2 terms. We have T1, T3, and this T2, T4 can be replaced by minus 1 by T1, T3. So this one, with the help of this, now is rewritten in this way. Now we are considering these 2 terms together, and then these 2, and then these 2. So first we will consider this. Now T1, T2 minus 1 by T1, T2, that is nothing but tan alpha by 2, tan beta by 2. Rewriting that, you get sin alpha by 2, sin beta by 2 divided by cos alpha by 2, cos beta by 2. And we need 1 by T1, T2. So that becomes, this will go to the numerator, that will come to the denominator. Now if you consider T1, T2 minus 1 by T1, T2, this minus this, when you take LCM, this is what you get, sin alpha by 2, sin beta by 2 the whole square, minus cos alpha by 2, cos beta by 2 the whole square. And whatever you have in the denominator, that is retained as such. Now we make use of this formula. Sin theta is nothing but 2 sin theta by 2 cos theta by 2. So using that, we get sin alpha by 2 cos alpha by 2 as sin alpha by 2. This is actually sin alpha by 2. Similarly, the next one, sin beta by 2. But this will go to the numerator, and that is what you have here. So you have accounted for the denominator. Now going to the numerator, you have it in the form a square minus b square. A square minus b square. So rewriting that as a minus b into a plus b. A minus b means what? This is a, this is b. A minus b means sin alpha by 2, sin beta by 2 minus a minus b. Cos alpha by 2, cos beta by 2. This term that we have. So how we can rewrite this as, we know that it is with the negative sign, cos a cos b minus sin a sin b, which is cos of a plus b. So here a stands for alpha by 2, b stands for beta by 2, and that minus sign is accounted here. So in the same way, for the other one, we have cos of alpha minus beta by 2. So further we can simplify this as this. The denominator remains as such, cos c cos d. So that is rewritten in terms of cos c plus cos d. C, actually c plus d by 2, c minus d by 2. So that is what we have. So writing the product as the sum. So using that technique, we have from this step to this step. Now this is obtained for the first term. In the same way, 2, 3 means you will have beta gamma. 1, 3 means you will have alpha, gamma. So we obtain all the 3 values for this to be this one. See here we want to supply the sine gamma, multiplying numerator and denominator by sine gamma. So the first term now becomes whatever here we have, that will be there, along with of course minus sign, but we are going to have 0 on the right side because in equation 3 you have 0 on the right side. That's using the relation between the roots and coefficients. So when we simplify this one will go to the right side, and that will not be there. And cos alpha, cos beta, sine gamma, cos beta, cos cyclically it comes. And we can club the terms cos alpha, sine gamma. Then cos gamma, sine alpha. So these two together, they will give sine of alpha plus gamma, this one. And in the same way we can club gamma beta, cos beta sine gamma, cos beta sine gamma, cos beta sine gamma, then cos gamma sine beta, this one. So that will give this. So in the what is remaining is nothing but sine of alpha plus beta. So you have the sum of this to be 0, and that's what we are supposed to establish. Now the next one, if the normals at 4 points x1, y1, x2, y2, x3, y3, x4, y4 on the ellipse are concurrent, if they pass through one particular point, then we are asked to show that sum of the abscissa and multiplied by sum of the reciprocal of the abscissa to be 4. So in this case, even though normals have come, we make use of the Cartesian form of equation of normal, Cartesian form. So far we have been using the parametric form. Now that we are going to use in this particular case, that has to be remembered. We need to consider the Cartesian form of equation of ellipse. So from equation 2 we get our y to be, taking everything to the other side, and this is what we get. And this is further simplified because a square minus b square, when we consider from here, it is so you have b square is equal to a square minus a square e square. So when you have a square minus b square, it can be replaced by a square e square. A square minus b square can be replaced by a square e square. So this becomes a square e square, but already one a square is there. Taking that out, you have h minus e square x. So that is your equation 3. Now that we are going to use in equation 1. That is x square by a square plus y square by b square equal to 1. So then substituting that on simplification, you will get 4th degree equation. So what is to be remembered in this is we have to consider the Cartesian form of equation of normal. Only then we can easily obtain what is required. So we have being the 4th degree equation, sum of the roots, sum of the product of the roots taken 2 at a time, sum of the product of the roots taken 3 at a time, product of the roots, all the relation between the roots and coefficients from theoretic equation we can easily write out. Now our job is to find summation xi, that is obviously present. Summation 1 by xi we need. So if we consider summation 1 by xi, it is 1 by x1 plus 1 by x2 plus 1 by x3 plus 1 by x4. So when we take LCM, we have in the denominator x1, x2, x3, x4. Coming to the numerator, you will have that to be summation x1, x2, x3. 4 terms will be there. This is what we have. And this is your S3 and this is your S4. Just substitute. On simplification, we get this. but already summation xi is known and this is known. So you have summation xi into summation 1 by xi to be 4. So that is what we are trying to establish. So the next we will have concyclic points.